Hi friends, this is PH4501 one-dimensional diatomic linear lattice and the lecture is taken by Dr. M.R. Gadhvi. In the previous sessions we have discussing about the linear lattice one-dimensional monoatomic case. Over here it's a diatomic case. You can look at the figure, one circle and one is a hollow circle and another is a solid circle. So that will giving us an indication that there is a two varieties of atom. One could be heavier, second one could be the lighter one. So at the odd atomic position there is a m1 or mass of that position, that would be m1, and even number position atom having the m2. So the periodicity of the atoms is achieved by the twice of atomic लेटिस लेंथ, दैट इज़ अ ट्वाइस ऑफ ए। माने अगर ये दो एटम के बीच का डिस्टेंस ए है तो यहाँ से यहाँ तक का डिस्टेंस कितना हो जाएगा, दैट इज़ ट्वाइस ऑफ ए। एनीवे, सो ओड नंबर हैविंग अ मास m1 एंड even number having a mass m2, that even speculated from the figure. In the last we had also noticed that we are assuming that force constant will be equivalent to the beta. The force constant can be written with the force, that is F is equal proportional to the displacement, and that is ultimately it is the F is equal to beta x, where x is the displacement. Let displacement of the atom from the nth position, that we are underlining as a equation of a displacement, and F is equal to, we can write it out, ma, that is mass and the associated acceleration. So we having a two different masses atom, a m1 and m2. So let's take the second derivative difference of displacement of the atoms, and that would be t square u2n plus 1 upon dt square. So what is the net displacement when the atoms are vibrating? When atoms do vibrating, naturally the atoms is, let us say, vibrating. अगर ये m1 vibrate हो रहा है तो you need to take a total displacement of this m1, and I may having a difference of the RHS side lattice variation and variation of the left side lattice variation of the atom, and therefore the difference between the beta x can be measured by the difference of preceding order of the atoms minus the difference of previous mode of atoms sequence. So in short, आप आगे के एटम के बारे में का डिफरेंस सोच सकते हो, एज वेल एज द पीछे के एटम के बारे में भी एटम सोच सकते हो. सो नेट डिफरेंस विल गिव यू अ नेट डिस्प्लेसमेंट, एंड देयरफॉर m1 d square u of 2n plus 1 dt square is equal to beta of u of 2n plus 2 plus un of 2n minus 2 twice of u of 2n plus 1. यहाँ पे इस तरह से याद सकते हैं, जिसका सेकंड डेरिवेटिव है दैट वुड बी मल्टीप्लाई बाई 2 एंड विद द नेगेटिव साइन इन द लास्ट इक्वेशन, वेयर एज दिस टू position, that is a preceding and the following up. So these two are the terminal points over there. Similarly for the m2, it becomes the d square u of 2m upon dt square is equal to beta of, ये आगे वाला माने 2n plus 1, ये पीछे वाला आइटम twice n minus 1 minus of twice of u2n twice of u2n, and therefore the solution of each displacement we can having a exponential I omega t minus 2n ka. So this is a solution of a solution of those vibrations, and because of vibration those waves are generated. So this is a solution of the wave. So now if you do remember, I do have a two equations. Equation 1 was d square u of 2n plus 1, or second में d square u of 2n. And with this, if you have a solution, then you can take the second derivative with respect to the needy equations for the twice of minus 1, twice n of plus 1, and so on. So that relation you can understand, and you can substitute at the position of the left hand side of the major equation, as well equation 1 and 2, as well as the right hand side. By giving a solution to this, we having the equation twice beta minus omega square m1 a1 minus twice of beta cos ka into a2 is equal to 0. Let us say equation number 4. And similarly we may have the relation with the m2, and that would be, यहाँ से याद रखने की ज़रूरत है, so that would be inverted, and that is this term become the first with the same sign, negative sign, so twice of beta cos ka a1, and this would be the additional part plus, माने ये term तो plus ही थी, twice of beta omega square m1 a1, so here will be m2 a2. So that way equation 4 and 5 will be appeared, and from equation 4 and 5 to get the solution we can take even the determinant. By taking a determinant, ultimately we are knowing the next point of argument is the final equation in the shape of omega square minus twice of beta m1 plus m2 upon m1 into m2 omega square plus 4 beta square sin square ka upon m1 m2. And with the solution to find it out the root for the above equation, so we can having a very clear picture about the wave occurred within the crystal, and that would be minus b plus or minus under root b square minus 4ac upon 2a. With this we having the equation 6, and that would be omega square is equal to beta of m1 m2 plus upon m1 m2 plus or minus beta under root of m1 plus m2 square upon m1 m2 minus 4ac, so that would be sin square ka upon m1 m2. So this way we are able to find it out the root. Now it is very clear that in the case of a root, जैसे कि 25 का root अगर आप निकालो तो +5 and the -5. So same way in the case of a square root of omega, we may having the two answers, but the negative answers cannot be acceptable, because ultimately we are finding out the omega on the basis of dispersive relations for a diatomic linear lattice. So we can have the idea of, rather than taking the negative component, we can do a solution with the equation 6. In the first term, the second term to be added, and the finding out the second value of the omega square, we do the other way, माने first term minus beta of the second term, and we are able to find it out there, maximize value and how it is damped and the importance of forbidden. So in the dispersive relation, there is a two particular branch is visualized. One corresponds to the omega minus, माने first factor is subtracted something by a certain factors, and that would be omega minus, called the acoustical branch, and the other corresponding to the omega plus 2, that is called the optical branch. The first Brillouin zone is referred as minus pi upon 2a to plus pi upon 2a. अगर ध्यान से देखा जाए तो the atoms are repeated by the interval of a twice of a. So अगर यहाँ की latest length ही आप ढूंढोगे, so that would be the k upon the periodicity of the atoms, so that would be twice of a, so it become a pi upon twice of a. And with this logic we may find it out the omega plus square माने addition of the second factor, and we found it out that omega plus is nothing but under root of twice of beta m2. सो इक्वेशन 7 अगर देखो तो ऑप्टिकल ब्रांच माने एडिटिव कंपोनेंट ऑफ द ओमेगा, और वो सिर्फ m2 और बीटा पे आधारभूत है. ओके, एंड सिमिलरली omega square minus indication is saying that the second square bracket is subtracted from the equation first one, so that is a beta of m1 plus m2 upon m1 m2. So with this logic you are able to get the omega minus is equal to under root of twice beta upon am1, and this is over here I am stopping, that ultimately we are able to find it out the omega plus, that is the maximum value of the optical branch, and this is a maximum value of the acoustical branch. It is more or less similar, it is more or less similar when you look to the graph. The upper high limit is under root of beta upon m1, whereas the highest limit for the optical branch, that would be twice of beta upon m2. And with this you can understand what exactly mean of omega plus, that is the optical branch, this is the acoustical branch. फिर से मैं आपको बताता हूँ, तो ये नीचे वाली है तो acoustical ब्रांच है, फिर forbidden है, फिर optical ब्रांच है. सो ऑप्टिकल ब्रांच का रिलेशन आ रहा है अंडर रूट ऑफ ट्वाइस बीटा m2, दैट मीन्स दिस इज डिपेंड ओनली ऑन टू पैरामीटर्स बीटा एंड द m2, वेयर एज द एकॉस्टिक ब्रांच का मैक्सिमम वैल्यू इज डिपेंड ऑन टू पैरामीटर्स, दैट इज अ बीटा एंड m1. I think 2 is missing here, please add over there. So it is there, and from that we have find it out the mathematical relations. Omega plus माने adding of two component, that would be under root of twice of beta m2, and the negative frequency or the second factor is going to be subtracted, then it would be omega minus or little bit less magnitude value, that would be twice of beta upon m1. With this I am stopping here. All the best wishes, stay home, stay safe.